We continue our discussion of solving trigonometric equations, and the two examples in this video involve an argument on my trig function, which is not just a theta, so how to handle that. So we start the same way we've done all of our trig equations by isolating the trig function. So if I add add 1 and divide by 2 to both sides, I get sine of 2 theta is equal to a half. Now, you can't do anything with that. I can't separate that. I can't divide by 2. The argument of my sine is 2 theta, and that's going to stay 2 theta. We're going to deal with that when we write out our general formula. So think about this as this is the sine of something is equal to a half. So what we want to do is identify what that something is. So that something, 2 theta, is equal to what? And that what are the angles where sine is equal to a half. So I'm thinking about my unit circle between 0 and 2 pi, where the sine value is equal to a half. I know that sine is positive in the first and the second quadrants, and I know that sine is equal to a half at my pi's over 6's. So I'm going to start with the first quadrant. 2 pi is equal to pi over 6, and then to finish out the general form, I'm going to add in that 2n pi. Now to finish this out, what I'm going to do is solve for theta. So now I'm going to get rid of that 2. Now that I have it out of the argument position of my trig function, I can divide out that 2. So if I divide everything by 2, and I would recommend thinking about each one of these individually divided by 2, I end up with a final general formula that says theta is equal to pi over 12 plus, here the 2's divide out, and I just get n pi. So my general form for that angle is pi over 12 plus n pi. And then don't forget we have another angle in quadrant 2 that has a sine value of 1/2. So I need to set up another equation. 2 theta equals 5 pi over 6 plus 2n pi. And then we're going to do the same thing. I'm going to divide each one of these terms individually by 2 to come up with my general formula that says theta is equal to 5 pi over 12 plus n pi. So there are the 2 general formulas that describe all of the solutions, the infinitely many solutions to this equation. Now, if I want to list some specific solutions, for example, I might be asked to list the solutions that only lie in the interval from 0 to 2 pi. So if I do that, what I need to do is what we've done in the past is identify different values of n. So if I start off and let n equal 0, start there, then I get 2 angles, pi over 12 and 5 pi over 12. And if I let n equal 1, I'm going to be adding pi to both of those, which would still keep me in that interval. And if I let n equal 1, I'm going to get 13 pi over 12. And if I add pi to this, I'm going to get 17 pi over 12. So there's 2 more solutions. Now, I wouldn't go beyond that, because if I let n equal 2, then I'm going to be adding 2 pi to both those angles, which would push me out of that interval. So if I only want the solutions in the interval from 0 to 2 pi, I just let n equal 0 and n equal 1, and there are my 4 solutions. Now, one thing to keep in mind too is that when we solved problems where our argument was a single theta, so if I had sine theta equals a half, and in this one we had sine of 2 theta equals a half, One thing to keep in mind that's helpful is to think that if I've got an argument that's just theta, then I know that there are two angles that have a sine value of a half. And if I'm dealing with an argument that's 2 theta, then that means I'm going to have twice as many. So I'm going to have 4 angles within that interval of 0 to 2 pi that have a sine value of a half. So that's kind of helpful if I'm asked to list all of the angles between 0 and 2 pi to know how many answers I should get. So since this was a 2 theta, there should be 4 angles in that interval with that sine value. Okay, let's take a look at another one. And in this one, notice that my argument is a little bit different. My argument this time is theta over 2. So if I'm solving this one now, my cosine is already alone on one side. So I'm ready to go straight to the thinking of the problem and writing my general formula. So this says the cosine of something is equal to a half. So I want to figure out what that something is. So that something is going to be any angles whose cosine is equal to a half. Now I know that cosine is positive in the first and the fourth quadrants, and cosine is a half at my pi's over 3's. So in the first quadrant, that would be pi over 3, and I want to add in my period multiple of 2n pi. And I also know that cosine is equal to a half in the fourth quadrant at 5 pi over 3, and then add in my period multiple of 2n pi. And now what I want to do is just rearrange these or rewrite these general forms so that I have theta alone on one side. So this time I've got theta divided by 2. So to get theta alone, I'm going to multiply both sides of my equation by 2. So that divides out my 2 there, giving me theta alone on one side. And on the right-hand side, I'm going to have my general form, 2 pi over 3 plus 4n pi. There's my first general formula for that. And over here, if I multiply the entire equation, meaning every single term, by 2, I get my other general formula, theta equals 10 pi over 3 plus 4n pi. So there is my general form. So if I'm looking at wanting some specific solutions here, let's say that you're asked to give, it seems like in my math lab they often ask for 6 specific solutions. Then we're just going to go through and replace our n's with integers. So if I let n equal 0, that's going to give me 2 solutions of 2 pi over 3 and 10 pi over 3. If I let n equal 1, I'll have to add 4 pi to each side, or to each angle. So that's going to give me the angles 14 pi over 3, and over here it would give me 22 pi over 3. And if I let n equal 2, then I would be adding 8 pi to each one of those angles. So 2 pi over 3 plus 8 pi would be 26 pi over 3. And finally, 10 pi over 3 plus 8 pi would give me 34 pi over 3. So there's 6 specific solutions to that equation.